welcome to this webinar, which is about markerless overlay and stitching to give you an idea what the webinar is about. So we will have an introduction. Then I will talk about stitching, overlay, mix and match, and finally some conclusions. Now, for the introduction, I just quickly summarize what NanoFrazor lithography is about. It's a direct write lithography based on the evaporation of a polymer resist, which is induced by scanning a hot tip in contact with the polymer. Key characteristics are 50 by 50 micrometer patterning space, sub 20 nanometer feature size, typically 1 millimeter per second scan speed, and importantly, we have built-in AFM topography imaging capability, which plays a big role in what I'm going to talk about. Now, stitching, overlay, mix and match are important concepts to enhance NanoFrazor lithography capabilities. If you ask Merriam-Webster for the meaning, you get these rather textile-centric explanations. The idea of the webinar is to put the terms into context with NanoFrazor lithography. So let's start with stitching. A typical problem you have in lithography is that the physical patterning space, 50 by 50 micrometer for the NanoFrazor, does not span the entire pattern which you would like to write. So what we then do is we decompose the target pattern into tiles which are sequentially written. And if we do it right, at the end, we will have the entire pattern. That's what we mean by stitching. Now, if we want to do that, we have to be a bit careful about the metrology in our tool. So we have two independent actuation systems, one for patterning and the other one is for sample positioning. And we have therefore also two frames, the patterning frame and the sample frame. Now, when we write, so we start writing the first field, then we move in our abstract patterning space to the second field, and in the physical space we do a translation with the sample stage. We not necessarily end up with a correct match, and likewise, if we then continue, we pick up more errors, and at the end we have a very ugly pattern due to stitching errors, and these can typically be avoided if you have accurate means to sort of make reference between the two frames, which if you want to do that accurately is a costly manner. Now, in the NanoFrazor, we do something different. So again, we start with our first field. We then select the second field. We move the sample stage to what we think is the correct position. We then take a topography image using the AFM of what we think is, in this case, the rightmost margin of the field, typically a micrometer wide, and then we compare it with what we would expect from the previously written topography, and we can do a cross correlation between the two meshed patterns, and that gives us a positioning error with about better than 10 nanometer accuracy. In the next step, we then shift the patterning frame to correct for positioning error, and we can write the next field, which is now accurately stitched after positioning error correction. This is what we do in the NanoFrazor, and this allows us to achieve excellent stitching capabilities. Here you see a test experiment which we did on our tool. So on the left frame, you see these L-shaped patterns, and on the right frame, you see what happens after we write the second L-shaped pattern, which is stitched to the corner of the first pattern using cross-correlation matching. And what you see in the red circles is sort of the overlay of our dial, which we have. And the second dial is what is called the vernier dial. So when the lines overlap, that tells you something about the error. And what we see is that all fields are within 10 nanometers from their nominal target position. Now, you can use stitching, as I explained, to write huge fields. And here is an example of an optical hologram, which is composed of 150 by 50 micrometer fields. The number of pixels which have been written is 10 to the 8. And okay, the patterning time is quite substantial, it's 10 hours. The hologram has virtually 0 errors, at least visible errors. And what you can see, it perfectly reproduces the Swiss Litho logo as it was initially intended to do. The third example I'm showing is something quite interesting which we can do on our tool. We can actually get the stitching correction just by looking at the polymer roughness. So we don't even need a written pattern to align different fields. And so what you see in the panel here, this is the initial frame we wrote. And then in blue, this is the bare polymer, which we then analyze. And here in this field, you see a typical roughness picture. And actually, this is unique for each area on the sample, and it can be used as a reference marker. So now when we write the second field, so for example, the one above, we inspect that area, make a cross correlation between what we measured for the first field and the second field. And then from the cross correlation peak, we can again extract the offset, which we made by moving the stages, correct for this, and get a perfect fit of these newly written patterns with respect to what we have written before. And the theory sort of says that you can get an error detection accuracy of, roughly speaking, 1.5 nanometers RMS by inspecting merely a 1 micrometer by 1 micrometer field. Now let's move on to overlay patterning. So what we mean by that is that we pattern something on top of existing structures. A simple example is here you would like to write electrical contacts and gates to a nanowire. So suppose you have this green nanowire here, then a lift-off stack that would be, for example, 50 nanometer of PMMA, and on top our patterning stack, we then form the openings for the metal lift-off, and then at the end we have the source, gate, and drain. Now the key thing, of course, is that we position our patterning right on top of the nanowire. And in principle, you can imagine that this is trivial, provided you can see the nanowire through the stack. If you can't see it, then you need to resort to some reference markers. introducing positioning accuracy problems as explained before. So now the big question is, what can we see through a resist stack? This is actually quite interesting. The physics behind it is rather involved, but it can be explained in very simple terms. So let's start with a substrate and a structure on top. Could be a nanowire, it could be a molybdenum disulfide flake. Now the important point is the structure should not be wider than about 20 micrometers. Otherwise this concept which I'm explaining here will not work. Now initially we start with a spin coating of our resist, and we end up with a flat surface. So as long as the resist is high, as long as we have a lot of solvent in the film, it is fluid, and then capillary forces will drive it to a flat surface. Now, as we wait, the solvent will evaporate, and as a result, the viscosity of the film starts to increase, and at the same time, the thickness of the film shrinks. Now, the capillary forces still would like to re-establish a flat surface, but because of the high value of the viscosity in the film, it cannot do so. And at the end, what we end up with is a replica of the substrate topography, which is reduced by some factor, basically the amount of shrinking of the film above the substrate. Now, you can do this in somewhat more mathematical terms. So the resist topography is given by the sample topography, convoluted by a transfer kernel, which can be approximated by a Gaussian profile. Now, the typical numbers here for this kernel are R, which is the reduction of the film thickness, is about 0.7. And the width of the profile is about 80 nanometers. And then when you think about it, you can write down these mathematical equations which tell you how much of the sample topography you will see on the film surface. If to make life a bit easier for you, I put in some typical examples. So a single wall carbon nanotube, it has a diameter between 0.5 and 1 nanometer. This is the lateral extension. The height is again 0.5 to 1 nanometer. You plug in the formula and you get roughly 5 picometers. Well, this, unfortunately, we cannot resolve with our tool. So let's go to a nanowire, 10 nanometer diameter, same story. And we recover about 0.45 nanometers of topography, which we actually easily can detect. Let's go to a single layer molybdenum disulfide flake. The lateral dimension is big now, it's 1 micrometer, say. The topography is very low, it's only 0.65 nanometers tall, but still we see 0.45 nanometer of contrast, which we can see. Now, as a last object, let's look at the nanoparticle, diameter 25 nanometers. And again, we would recover about 0.45 nanometers of topography, which we can see. On the left down here, you can see an actual example. This is a 25 nanometer nanowire, and the topography amplitude is 2.9 nanometer, exactly as you would expect from this very simple formula. Now, let's go to the first example. So what we are trying to do here is to write gate contacts to an indium arsenide core shell nanowire. Now, this nanowire consists of an indium arsenide core and the 5 nanometer aluminum oxide insulating layer. So when you try to fabricate this FET, you first have to write the source and drain contacts, remove the aluminum oxide, put the metal down, go back, respin, and then you can place your gate around the nanowire without opening the aluminum oxide. But the problem at IBM at that time was that the people tried to do this using ETH lithography, and they could perfectly write the drain source contacts, but whenever they tried to write the gate, the FET would not work because the channel was totally quenched by residual charges that were created by the high energy electrons during patterning. So they approached us, and we then patterned these gate lines here using the NanoFrazor, using our overlay capability, and sure enough, we then could recover a nice FET behavior, no gate oxide charging, a very low value for the gate potential to completely turn on the FET. So this worked extremely well. What we also did using the NanoFrazor, we also tried to fabricate a ballistic conduction channel in the indium arsenide, and we managed to do so in the shortest channel here, which behaved almost like a perfect ballistic channel with a transmission probability of, roughly speaking, 95%, which is extraordinary. Now, the second example is again concerning nanowires. Here, the goal was to accurately position electrodes to the edges of the nanowire. And the way it is done is we image the nanowire. It's a metal nanowire in this case. We applied the edge detection algorithm, then overlaid the electrode masks with the nanowire, wrote the structure, did the metal deposition, and you see the result after the entire process. The third example concerns now 2D materials. As I said, it's very easy to see these molybdenum disulfide flakes within the topographic signal, as you can see here very nicely. Now, in this case, what they ask us to do is to write an array of nanowires with a width of below 20 nanometers, which would act as conduction channels between between these metal contacts. And we actually could do that in a rather straightforward manner, just because we can see where we do the patterning, and that helps a lot to speed up the manufacturing process. Here is another example where we put the grating superstructure on top of a molybdenum disulfide flake, and the idea there was to tune the optical properties by imposing a periodic potential on top of this molybdenum disulfide material. Now, the last example, I would like to discuss mix and match, which is in essence combining different lithography techniques, in our case laser and thermal scanning probe lithography. The idea behind it is that we can use fast laser writing for coarse structures and TSBL patterning for structures requiring higher resolution lithography. The example which I show here is a single electron memory cell. It's made of silicon monoxide substrate, which is pre-structured by photolithography. What you can see here is the pre-structured sample, the task to do was to overlay a pattern which is shown here in this rectangle, unwritten rectangle. And as I said, we did that in 2 steps. We wrote the larger wires, which you can see here, with the laser, and the high resolution structures here, which are needed to form this single electron memory cell using TSPL. And the unique thing here is that we can use exactly the same resist for laser patterning and thermal writing. And that speeds up everything enormously, because normally what you have to do in mix and match lithography, you actually, for example, you first write with the laser, you go out to the lab, do the development, come back, and then you do, for example, the TSPL patterning by, again, putting a resist down. We don't need that. So here you can see a video of the laser patterning. It's real time. And you can see how these wire structures emerge. And then once this has been written, we would then put these fine-grained structures by overlay patterning into these rectangles. And here you can see the result of the final device. So I'm ready to conclude. So we can say that we can achieve 10 nanometer stitching accuracy between adjacent fields using cross-correlation techniques for determining field offsets, which we then apply to, well, we apply AFM topography imaging for determining these offsets. The overlay patterning is made easy, as in most cases, one can directly see the reference structure buried underneath the resist stack. And finally, mix and match lithography using high resolution TSPL and fast laser writing is holistically integrated, since one and the same resist stack can be used for both writing techniques without the need for in-situ development. So with that, the webinar is open for Q&A.